In this video, I'll go through the process of showing how to predict the product of a condensation reaction. So condensation reactions are the general classification when dealing with reactions that involve two or more organic compounds that chemically combine to form one larger compound, but during that process they release water. There are different types of condensation reactions, and those can be classified based on the product that is formed. For example, you have esterification, which simply means that the result of that condensation reaction is an ester. You also have the thioesterification, which means that the result of that condensation is a thioester. And then there is also the amidation, which means the result of that condensation reaction is the amide. And so in this case, we're looking at starting with a carboxylic acid and an alcohol. During this reaction, it often involves the use of an acid catalyst such as sulfuric acid. So you may see the word acid, you may see the word catalyst, you may see H+, or you may see the chemical formula for a specific strong acid. That catalyst helps to promote that chemical reaction and allowing the rate to increase so that it can occur at a much faster pace. But regardless, when we're looking at condensation reactions, they all occur essentially the same way. They involve parts breaking off of each individual reactant, and then those two pieces, the organic pieces, then combine to form a larger compound, while the other parts combine to form water. So let's go through and look at what takes place. And so anytime chemical reactions take place, it involves breaking old bonds so that new bonds can form. So when we're breaking old bonds, the bonds that are broken are the bonds that are more reactive, the bonds that have the most stress or the most tension, or that are the most unhappy because those electrons are not evenly shared or evenly distributed throughout the molecule. And so I'll redraw both reactants by showing the bonds that are present. So when you see that OH written like that, that's the same thing as saying you have a bond between that oxygen and hydrogen. I'll show the other. When you see that OH, same thing, a bond between the oxygen and hydrogen. Now what I actually recommend, because what you'll see when dealing with different chemical reactions involving organic compounds, the functional group is the site of reactivity for those compounds. I recommend that you actually have the functional groups pointing towards one another because it'll help you keep track of what's what. You don't have to do that, but it's a good way to make sure that you are following the process of that reaction. So I'm just going to erase this and redraw it, and it's going to still represent the same molecule, but it's just going to be flipped the opposite way. So I still have my OH. That oxygen has 1, 2, 3 carbon atoms. So I'm still going to show 1, 2, 3 carbon atoms. Same molecule. But now I can see the bonds that are present. And so when trying to predict which bond breaks, we can think about polarity. Polarity tells us that the electrons between these atoms are not equally shared. So those atoms aren't as happy being paired together as if they were forming nonpolar covalent bonds. So in this compound, this carboxylic acid, we have a carbon-carbon bond. There's no difference in electronegativity. That bond is a nonpolar covalent bond. But we have a carbon-oxygen bond. Carbon-oxygen double and single bonds present. And so in that case, we have polar bonds. So that means that the electrons are not evenly shared between those atoms. Instead, since oxygen is way more electronegative, it's able to pull harder on those electrons. So that oxygen is attracting the electrons in those bonds. Same thing with the oxygen-hydrogen. This bond is even more polar than the carbon-oxygen. So there's an even more uneven distribution of electrons. Same thing applies to this oxygen-hydrogen. So once you know that oxygen-hydrogen bonds are polar, regardless of what compound we're looking at, that bond is going to be polar. So those electrons are going to be attracted or being pulled towards that oxygen. So looking at the carboxylic acid, so I can just label these as A, B, and C. So typically when you have an uneven distribution, that makes the bond weaker or more reactive because those atoms aren't happy being paired that way. So we have all three of these bonds that I have labeled are polar. So they're all having that uneven distribution of electrons. However, one bond is going to be much quicker or much faster to be broken than the others. And so the reason why has to deal with, again, the atoms being unhappy being paired the way that they are. And so if we look at the carbon-oxygen bond, we have a double and a single bond. But it's the same carbon that's bonded to two different oxygens. So that same carbon is being pulled two different directions. That weakens that carbon. It puts more stress, more tension on it, and so it's not happy. If it could get rid of one of those oxygen atoms or one of those oxygen bonds, then it will be a little happier because it's not being pulled two different ways. At that time, it will only be pulled one way. And so chances are the carbon-oxygen bond is the bond to break. But which one? The single or the double? As you start increasing the number of bonds between atoms, those bonds become stronger. The stronger the bond, the more energy it's going to be needed to break the bond. The more energy that's needed, by the time you supply enough energy to break that bond, that was already enough energy to break a weaker bond. And so chances are by the time you break this double bond, the single bond would have already broken. So we would have already gotten rid of that bond. So because of that carbon being pulled two different directions, that weakens the bond and makes it more reactive. Because by getting rid of one of those carbon-oxygen bonds, now it's being pulled only in one direction instead of two different directions. If we look at the opposite compound, the alcohol, we have oxygen, hydrogen, we have carbon, oxygen. We don't have an atom being pulled two different ways. And so in that case, we can think about which atom or which bond would result in the atom being the most unhappy. So we have the oxygen and hydrogen versus the carbon and oxygen. Oxygen is happy because it's trying to take electrons. But carbon has a higher electronegativity value than hydrogen. So carbon is able to attract the electrons a little more than that hydrogen. Or you can think about it as a tug of war. So we could think about a tug of war between an elementary student and a high school student. The hydrogen would represent the elementary student. The carbon would represent the high school student. Chances are, if you were playing tug of war, then you would be able to easily win over that kindergartner or that elementary student. And so, because of how uneven the distribution is, it weakens that bond. So as a result, this bond is going to be more willing to break, so it's not going to require as much energy because that hydrogen is not as happy being paired with that oxygen as that carbon is being paired with the oxygen. Neither one is able to keep their electrons. The oxygen is trying to take both, but the hydrogen is in a losing battle. It's not as strong as that carbon, so it's losing those electrons. So if it could be away from that oxygen, that's what would happen. And so we broke off two pieces. You could show those two pieces boxed off. You could just do the little line to show that the bond broke. I'm just going to box them all together. Because what I've boxed all together represents an H and an OH. So I just boxed off two hydrogen and one oxygen. I boxed off water. During the condensation reaction, water is a product. So now just imagine that this water molecule was lifted up. And you can see how outside of my boxed area, this carbon still has its half of a bond. This oxygen still has its half of a bond. And so what ends up happening is that that carbon takes that half of a bond along with the oxygen. And that half of a bond, they come together to make a whole bond. And so we'll end up with this compound. You can also redraw it by putting those pieces closer together and simply drawing a new bond between that carbon and that oxygen. So we now have our two products. We now have an ester, and we have our water. So in this specific condensation reaction that occurred between a carboxylic acid and an alcohol, it would actually represent an esterification because we produced the ester. And so when you're looking at those products, and it'll always be the same thing. The hydroxyl from your carboxylic acid functional group and the hydrogen from your alcohol, this is where your water comes from. The two end pieces then combine to make the one larger compound. So we can look at another example. So let's say we have this compound. Tell you what, instead of the OH, let's do a different one. Let's just make it an amine. And what you'll see is still going to be the same process. We still have a carboxylic acid, but now instead of an alcohol, we have an amine. So with the condensation reaction, you're going to see your carboxylic acid, but then you'll also see a carbon heteroatom functional group. So we can still go through that same process. We'll see where still end up losing that OH from our carboxylic acid. But now with that nitrogen of the amine, so that NH2, so I'll just go ahead and draw out both hydrogen atoms. NH2 simply means that that nitrogen has two hydrogen attached. So it has a 2 hydrogen and it's bonded to that carbon. And so just as we box off that hydroxyl, I can just box off one of those nitrogen. That's where your water comes from. So when I show that product, I have water from my boxed area because I have H2O. What was left, so the opposite end would combine again. If you're trying to draw the structure, you can draw the individual pieces. I can show that I had this nitrogen. You can show that hydrogen. You can still show that it had a bond, 2 carbon atoms. You can either write it as an H or you can draw the bond to the H. But now these two end up connecting. So now we've gone from a carboxylic acid and an amine to an amide. So this condensation reaction represented amidation. And so what you'll see with the condensation reaction, regardless of whether our second component is an amine, as we have here, an alcohol, as we had in the first example, or a thiol, and remember the thiol is when you have the sulfur with the hydrogen, so the sulfhydryl group. So regardless of which we have present, the process is going to be the same. That hydroxyl group from your carboxylic acid would break off. A hydrogen from either the amine, the thiol, or the alcohol will remove, and then the two pieces remaining end up connecting while water was also formed. So this is the result of the condensation between a carboxylic acid and a second component.